Hi everyone, welcome back to MATA35. This is the end of week 11 of class. There are only 12 weeks, and today's class will cover basically all of the new math that we're going to be covering in this class. Next week will be application and review of the mathematical concepts that we have been working on over the course of the semester. So what we're going to be doing is we're going to be talking about power series today, and so we're going to do this a little bit more intuitively to try to explain and we're going to be using power series to explain some of the techniques that we covered briefly and I just gave you the theorem for, but I didn't actually prove. So let's start by talking a little bit about, well, mathematical operations. So let's start with an easy question for everyone in chat. Which of these mathematical operations is the hardest? And let me reset. So let's see, what do people find difficult? Well, it looks like we have a lot of answers for D, for division. And a couple people said all are equally hard. Okay, so this is of course a very subjective question, right? Because, well, maybe addition is easier for some people than multiplication. Maybe for some people multiplication and division are equally hard. Now, there are ways of formalizing this idea of hardness, though, and one of the ways you can formalize it is to think about which operations are well defined for all questions. So, in particular, adding, subtracting, or multiplying two real numbers always gives you a real number. So, for example, 5 plus 3 is 8. That's something we all know. 3 minus 5 is minus 2. That's still a real number. It's negative, which makes it slightly more complicated, but it's not too bad. 4 times 0 is equal to 0, and even things like pi times e are real numbers. And so adding, subtracting, or multiplying together things still gives you a real number. But, as you all know, dividing two real numbers may not. So things like 4 divided by 5, that's equal to 0.8, so that is a real number, but 4 divided by 0 is not a number. And so this is not well defined as a number. You can make this formal. You can talk about things like the extended real line, but this is one of the formal ways that you can argue that division is harder than addition, subtraction, and multiplication because you don't always get an answer, or you don't always get a well-defined answer. So now this is basically another thing that you might notice is that addition and subtraction are basically the same because you can just subtract by the negative of a number, or add the negative of a number to approximate subtraction. Whereas that doesn't work for division because you can't always multiply by the inverse of a number because the inverse of 0 is not defined. So this really gets at the basic building blocks of mathematics. So somehow addition, subtraction, and multiplication are more basic than division. And that brings us to what a polynomial is. So many of you guys are familiar with polynomials. We've been using them throughout the course. You guys have probably seen them since pre-calculus. But let's think about polynomials a bit more intuitively. So a real polynomial is, let's call it p of x, in a variable x, is an expression that combines together x with real numbers using just addition, subtraction, and multiplication, but no division. So, for example, what just happened? Yeah. So, for example, we might have a polynomial, which is p of x is equal to x plus 1 times x minus 1 plus 5 times x minus 3.4x plus 5. Right? So you're just combining together a bunch of real numbers and copies of x using addition, subtraction, and multiplication, but no division. Whereas something like this here, f of x is equal to 1 over x. Oh, what just happened? I skipped forward a couple of pages. Let's go back. So f of x is equal to 1 over x minus 1. Well, this is not a polynomial because you have a division here, dividing by 1 over, you're dividing by x minus 1. Or you have f of x is equal to e to the x. Well, this also isn't just a multiplication, subtraction, or division. So you can think of exponentiation as repeated multiplication, but it only works if you're doing it an integer number of times, right? And so e to the x, well, that's not a polynomial. Or things that are more complicated, like f of x is equal to, say, ln of x times x squared. That's also not a polynomial. One nice thing about polynomials is that we can always write them in a canonical form. So we had this complicated polynomial above. We can write this in this form: an x to the n plus a some an minus 1 x to the n minus 1 plus dot 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 a1x plus a naught, where each of our ai's is a real number and n is a positive integer. Because if you take x to an integer power, well, that is still you can construct that by just multiplying n times. So, for example, for the polynomial we had above, we have p of x. If you multiply it all out, you get x squared minus 1 plus 5x squared minus 3.4x plus pi. And this is equal to 6x squared plus minus 3.4x plus pi minus 1. Okay, so even though we constructed so polynomials can't have negative exponents. Exactly. So polynomials cannot have negative exponents. If you have a negative exponent, then it becomes not a polynomial anymore. And we'll see this pretty soon. But basically, negative exponents correspond to division, right? And there are some nice properties of polynomials that are lost once you have division. But yeah, so, well, we started with this idea, oh, well, polynomials are everything you can construct using addition, subtraction, and multiplication. And then we realized that we didn't prove this, but it's pretty easy to see that whenever you have a construction that's of x and real numbers with addition, subtraction, and multiplication, you get something that you can write in this form, an to the x to the n plus dot 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 through a naught. And this canonical form is nice, and this is probably how you were introduced to polynomials if you've formally seen them before, which is you write them down in this form where you have integer powers of x times some real number. Okay, so what do we mean by the statement that polynomials are nice? Well, again, polynomials are built up from these easy operations of addition and multiplication. Well, and implicitly subtraction, but that's just adding by minus 1 times a real number. So we don't really need to include it explicitly. And one of the nice things is if you add together two polynomials, you get another polynomial. So let's say p of x is equal to x squared plus 2x plus 1. That's a polynomial. Let's say q of x is equal to x cubed minus 1. That's a polynomial. Well, then p of x plus q of x is also a polynomial. In this case, it's equal to x cubed plus x squared plus 2x. Okay, well, and I mean, we can add together two polynomials. You can also multiply together two polynomials. So if you multiply together these two polynomials, you get p of x, q of x. Well, you have to expand out, and so it turns out when you expand out, you get x to the 5th plus 2x to the 4th plus x cubed minus x squared minus 2x minus 1. So this is still a polynomial, and this is true for any two polynomials that you multiply together. There are a couple other nice properties. One of the important ones is that polynomials are infinitely smooth. What does this mean? Well, intuitively it means that you can draw a curve and there are no kinks in the curve. But infinitely smooth more formally means that you can keep on taking derivatives at any point and the derivatives are always well defined. In fact, we can even say more than that, which is that if we have, say, p prime of x is going to be equal to 2x plus 2 using p of x is equal to x squared plus 2x plus 1, well, p double prime of x is going to be equal to 2, and p triple prime of x is equal to 0, p fourth derivative is equal to 0, and so on. Those are all equal to 0. Whereas there are examples of functions that are not polynomials, so non-example. If you have something like f of x is equal to the absolute value of x, so that looks something like this, with a kink here, then f prime of x is equal to minus 1 if x is less than 0, 1 if x is greater than 0, and undefined if x is equal to 0. And so this is an example of a not smooth function. And so this is one of the ways that you can see that the absolute value of x is not a polynomial. Any questions so far on like what we mean by polynomials? So when we say polynomials are smooth, we're talking about the fact that they don't have holes or asymptotes. Yeah, basically. So that's basically what we mean. So they don't have holes, they don't have kinks, they don't go off to infinity all of a sudden, they don't move around super duper fast either. So there are all sorts of functions that you could define. You could define a function that is super duper random, basically. For each number, you assign it to some random number or things like that. You can define a function that way. They're not very nice functions. In fact, they're really terribly not nice functions. And those aren't polynomials, and they're also not smooth. So you can have smooth functions that are not polynomials, but polynomials are an example of smooth functions. And if you ever take a mathematical analysis class, this is something that's really quite important. Okay, so now what exactly is a function with a kink? Yeah, like a sharp turn. So that's why I use this example here. So like this here, it doesn't go smoothly through that point. It hits it and then it jumps in a different direction. And so at a point here, you have a tangent line, but at a point here, well, what's the tangent line? Is it here? Is it here? Is it there? You don't actually know. And so that's what we mean by a sharp turn or a kink. And the more formal way of saying this is that the derivative at that point is not well defined. In some cases, you might have things that are somewhat smooth. You might have a function that has a first derivative but not a second derivative. And so that's not infinitely smooth, because even if the first derivative is continuous and exists everywhere, the second derivative might not. And so it's not infinitely smooth. Basically, you can think of smoothness as just a generalization of continuous. So something that's continuous and all its derivatives are continuous. Okay, so now we've formally talked about this, let's go back and think about one of the other things we covered back in weeks, I want to say around week 6. So we talked about regression. And so what did we do when we talked about regression? Well, one of the things we did is, well, we started with linear regression, which is basically given a bunch of data, we want to find things that look like lines. We also talked about quadratic regression, which is given a bunch of data, we want to find some function that looks like a parabola that fits their data. We had cubic regression, which are things like lat. But then we also kept on going, and we had arbitrary polynomial regression. So you notice that this is a slightly different form than we just wrote out, but where we basically have some polynomial, and you can add more parameters, and add more parameters for better fit. Because the whole goal of this was to fit a function to our data. And we also, of course, had our exponential and power dependency regressions, but we're not going to talk about them too much. What we care about today is these polynomial regressions. So what was the point of polynomial regression? Well, it was just that given a collection of points, we can approximate it with a polynomial function. So let's say that we had we have a bunch of points. Well, a line might fit terribly. So maybe lines fit terribly in this case. Terribly. Well, you can try doing a quadratic fit. So a quadratic fits better. And something like a cubic might fit even better. Cubic fits even better. So as you add more parameters, you can approximate a collection of points better and better. Still, one of the caveats that we mentioned when we talked about polynomial regression is that although you can fit things better and lower your mean squared error, sometimes you're going to overfit. So, for example, if you had just a series of points, let's say here, 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 well, maybe a line works well, but maybe you can overfit by just having some complicated polynomial that does something like that. So this is a better fit using more parameters. For real data, you have to worry about overfitting. But the basic idea is that you can approximate data with data points with a higher order polynomial function. Actually, let me continue listing count this way. So that's probably more likely. So now the question is, well, if we can fit data using a polynomial, what about other functions? So sometimes another nice function looks almost like a polynomial, at least locally. And so if you think about it, what we're basically doing is the same task as regression. So let's say we have, I'm going to use sine of x. So let's see if I can draw out sine of x. Okay, so this is sine of x. Let's say this is the x-axis and this is the y-axis. So we have sine of x, and what we'd like to do is we'd like to find a polynomial to fit to this data. And there are a couple of choices you might start with. So let's start with a first-degree polynomial. What happens if we approximate this with the function y equals x? Well, this here is actually a, if you look closely around the origin, this function does seem to be pretty close to the sine function. Now, of course, as with polynomial regression, if we want to fit things even better, one of the things we can do is we can increase the number of polynomial terms. So that increases the number of parameters. And it turns out that there is, let's see if I can draw this. So if you wrote out the function y is equal to x minus x cubed over 6, this starts to fit it even better. And in fact, if you think about the sine function as just a collection of data points, you can imagine that if you had added enough polynomial terms to your regression analysis, you could fit a polynomial that looks almost like the sine function for a large number of points. And that's one of the goals we have, because polynomials are nice. And so if we can come up with a polynomial that approximates these other functions, then we can work with that and do addition, multiplication, and other things of that sort. Okay, so that's the basic setup of what we're talking about today. So what we did is we figured out that addition and multiplication are easy operations, and that's why we define these polynomials the way we do. Why can it not exactly fit the sine function? That's a very good question. So can you have a polynomial that exactly fits the sine function? Well, if two functions are the same, then one thing that you'll notice is that why do we consider sine and cosine to behave in the same smooth way? Yes. So what did we mean by smooth? We meant that you could take derivatives infinitely and they're well defined. Well, if you start with the sine function, let's say we have f of x is equal to sine x. Well, we can take f prime of x, that's equal to cosine x. F double prime of x is equal to minus sine x. F triple prime of x is equal to minus cosine of x. And then f to the fourth derivative of x is equal to sine x. And in fact, it keeps on repeating. So if you keep on taking derivatives, you end up just cycling through all of these. But you'll notice that each of these derivatives is well defined. So you can keep on taking derivatives forever, and it's well defined everywhere. And so, therefore, sine and cosine, as you can see from this chain of derivatives, both you can take derivatives infinitely. And so that's why we consider it to be smooth. But on the other hand, if you look at these derivatives, if you have any polynomial and you take enough derivatives, it's going to be equal to 0, right? Because whenever you take the derivative of a polynomial, it reduces the order by 1. Or by at least 1. Unless the order is already 0, of course. And so, therefore, you know A, that you can't write sine as a polynomial, and B, you know that sine is also smooth. But of course, if you add more polynomials, you might be able to get something that fits even better. So I don't actually know the equation for it, but maybe you could come up with something that looks like that. Maybe there's some fourth order polynomial that looks like that you could fit. If you add more polynomials, will it become a straight line? if you as you add more and more polynomials, you get closer and closer to the sign function. I mean, if you add the right polynomials, of course. So, sort of like with our linear, polynomial regression, if you add more and more points, you fit more and more closely to your data set. And here, our data set is the sign function. That is a great question, Samantha. Thank you so much for asking. So, what is a formal power series? A polynomial we can write in this form. It's some sum from I equals 0 to n of ai x to the I. So for example, this is something that is finite. So for example, you might have p of x is equal to 1 plus x squared plus x cubed. A formal power series is the infinite sum where n goes to infinity of these summations. So for example, you might have p of x is equal to 1 plus x squared plus x cubed plus dot 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 all the way to infinity, which you can also write as I equals 0 to the sum from I equals 0 to infinity of xi. And so the answer to your question is that yes, you can actually write psi as an infinite sum of polynomials. You can't write it as any finite sum, but you can write it as an infinite sum of polynomials. And this, of course, gets a little bit complicated because whenever you're dealing with infinite sums, well, then you have to deal with things like convergence. And so I can write down an infinite sum, but it doesn't necessarily converge to a limit as n goes to infinity. Sometimes it converges, sometimes it doesn't. A formal power series, you can write down the sum, but it doesn't always necessarily have an answer. So in the example I gave earlier, so on the previous slide, we had p of x is equal to this infinite sum, I equals 0 to infinity of 1 plus x plus, that's xi, which is equal to 1 plus x squared plus x cubed plus x to the fourth, so on, all the way to infinity. So you might ask, does this converge at a particular point? So does this converge at the point p of 1/2? And that is a question for y'all. And let me reset before you answer. So does it converge? If it converges, does it converge to a number, or is it divergent? Okay, so it looks like you guys recognize this. So this is indeed a geometric series. And if we write this out, what you get is that this is equal to 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot dot dot. And this is actually equal to 2. Okay? And so this is actually convergent, and this power series converges at the value 1/2. What about if we do something slightly different? What about p of 1? What's that equal to? And let me reset before you reply. Okay. Yeah, so the answer here is, well, this is equal to 1 plus 1 plus 1 plus 1 plus dot dot dot, an infinite number of 1s. And this is unfortunately divergent. Because even though we wrote out this power series only converges to a real number for certain cases. In fact, you may notice that this is precisely a geometric series. And so what we have is if the absolute value of x is less than 1, then we know that p of x is equal to 1 over 1 minus x. And this is just because this is a geometric series. And we know that if this is greater than or equal to 1, then p of x is divergent. I don't understand. Okay. So Did you guys not study limits and convergence in MAT35? So what we're basically saying is that this summation, and let me explain it intuitively. So basically what we're doing is we have 1 plus 1/2, so that's 1 plus 1/2 is equal to 1.5. Okay, so basically what we have is if we take 1 plus 1/2, that's 1.5. If you take 1 plus 1/2 plus 1/4, that's 1.75. If you take 1 plus 1/2 plus 1/4 plus 1/8, that's 1.875, and so on. And it turns out that as you take additional terms of the summation, it gets closer and closer to 2. And in fact reaches it as you take an infinite number of pieces. Intuitively, basically, what each time you're halving the distance from 0 to 2. More precisely, the sum from I equals 0 to infinity of ai xi is equal to the limit as n goes to infinity of the sum from I equals 0 to n of ai xi. Okay, so basically what you're doing is you're taking a infinite sum and you're converting it into this limit as n goes to infinity of, that should be a finite sum. Of this finite sum of just the first n terms. It can never get to 2 because it's always adding a fraction, not a full one. Yes, but it is adding an infinite number of these fractions, and so eventually you get to, at time infinity, if you were able to go on to infinity, it would get to 2. The way to think about it is, it can get arbitrarily close to 2. So, as time goes to infinity, it's always getting closer and closer to 2. And so that's what we mean by convergent. Okay, and we also had a question of what is a geometric series? So a geometric series is precisely adding together things like where you're taking some ratio to some power. So things like 1 plus 1/3 plus 1/9 plus 1/27, things like that, and so on. That's a geometric series. Okay, so let's see. I am going to go on for now, but if you guys have any more questions about this, let's talk about it a little bit more in the break or after class. And if this is a question that a lot of people have, I can spend some time on Friday covering this in a little bit more detail. I should go ahead and mention that a lot of the stuff I'm covering right now is, what's the right way of putting it? A lot of the stuff I'm covering right now I don't expect you to fully understand for the exam. I may have questions about it, but it won't require a full understanding of how the convergence properties, just because that's not something we're going to cover in detail. But let's talk about it in the break. The basic idea that you should just keep in mind is sometimes when you add together an infinite number of things, you end up getting a real number. Sometimes when you add together an infinite number of things, you don't end up getting a real number and it diverges in some way or another. So another example of divergence is if you have p of -1, that's equal to 1 minus 1, minus 1 plus, 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. And you'll see that fraction keeps on flipping between 0 and 1, and so it doesn't converge to a single number. So this is also divergent. And unfortunately, I don't have all the notes prepared for that, so ask me questions about that later. No. So geometric series is a particular kind of convergent series. It is a specific type of convergent series where each term in the series that you're adding is the previous term multiplied by some number. There are other series that are also convergent. And these are things that you can prove the convergence of these things via things like the squeeze theorem or some of the other theorems you covered in MAT35. But for now, let's not worry too much about convergence and just talk about what we mean by these power series. So when you are talking about these formal power series, they do have some interval of convergence where if you plug in the number, it makes sense and you get a number out of it. And so you can think of a formal power series as a function whose domain is the interval of convergence. What do we mean by that? What we mean, and you should take this on faith for now, but if you have the example p of x is equal to 1 plus x squared plus x cubed plus x to the fourth, dot, dot, dot. Well, this is a function on the domain minus 1 to 1. What do we mean by that? We mean that this function is only well defined when the series converges. So if x is equal to 5, well, this p of x doesn't ever converge to a real number, and therefore this function isn't well defined at the point 5. But it is well defined at the point 0.5, since p of 0.5 is just equal to 2. So these power series, you can think of them as restricted functions that work on some domain. It turns out that sometimes you can express another function as a power series, at least on some interval of convergence. So for example, if you had x squared plus 2x plus 1, this is a polynomial, and already a power series. Because you can rewrite this as x squared plus 2x plus 1 is equal to the sum from I equal 0 to infinity of ai x to the I, where a0 is equal to 1, a1 is equal to 2, a3 is equal to a2 is equal to 1, and then a3 is equal to 0, so on. Also, it turns out that 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x to the fourth, and so on the interval minus 1, 1. So what we're saying is that we now have two different ways of, if we restrict x to be being between minus 1 and 1, then we have two different ways of writing this function 1 over 1 minus x. One of the ways is to write it out as 1 over 1 minus x, and another way is to write it out as this infinite power series. Now, of course, there are some disadvantages of writing it as an infinite series. I don't know if it's just me, but this slide doesn't make much sense to me. Okay, that is, do you mind saying which parts didn't make sense? Let me try explaining it again, since I think I had mistakenly assumed that you guys had more background in series and limits than it seems like you all do. So let me try again. So we've defined this infinite sum, right? So one of the things that we did is we defined this infinite sum. Oh, come on. We defined this infinite sum. P of x is equal to 1 plus x squared plus x cubed plus x to the fourth. So now, we define it in some infinite sum, and sometimes this infinite sum results in a real number, right? So if x is equal to 0.5, then this infinite sum is equal to 2. If x is equal to 1/3, then this infinite sum is equal to 1.5? I think it's 1.5. Yeah, so for some number of possible x's, this is a function, because it takes a number and sends it to another number, right? Because remember, a function is just something that takes a real number and sends it to another real number. And so we have this operation that takes a real number, assuming that that real number is between minus 1 and 1, and sends it to some other real number, and therefore it's a function. Is everyone all right with that? So we have a function so functions are things that send one number to another number. And this power series, this formal power series, sometimes sends one number to another number. Sometimes it doesn't, right? So it's not well defined if x is greater than 1, because then it no longer sends a number to another number. Instead, it sends a number to something undefined. So for example, if you think about it, you have a function f of x is equal to 1 over x. This function is well defined whenever x is not equal to 0, right? Because it will send a number to another number so long as x is not equal to 0. But if x is equal to 0, then it's no longer well defined, and therefore it's only a function on the domain where it sends one number to another number. This function p of x here, this power series, is even more restrictive. So it only sends one number to another number if you're in this interval where that x is between -1 and 1. If you're outside of that interval, then it no longer sends one number to another number, and therefore it's not well defined on for x is equal to 3 or 4. So basically what we're saying is that we've defined a very specific sort of funny looking function based on taking these infinite sums of terms. And so since this is a function, you might ask, well, maybe this power series is another way of writing a function we already know. Or if you have some other complicated function we already know, can you write it as a power series? Well, for some functions, it's pretty easy, right? So if you have a function that's a polynomial, well, that's already a power series. And so that's what this first example was showing. So that any polynomial is already a power series everywhere, basically, because that's basically we're defining power series as generalizations of polynomials. Other times, though, if you have some function say something like 1 over 1 minus x, you can write it as a power series, though it may not always. The convergence of the power series may limit where this function is well defined. So 1 over 1 minus x is well defined everywhere except for x is equal to 1. But the power series is only defined when x is between -1 and 1. Did that clarify things a little bit? The basic idea here is just that sometimes you can express another function as a power series. And that turns out to be really, really useful for a whole host of reasons. Okay, hopefully that explained things a little bit better. Let me move on, and if you still have questions, ask me in the break or during off. Oh, can you just repeat the last part about the domain of -1 to 1? So if x is in between -1 and 1, 1 over 1 minus x is equal to 1 plus x squared plus ... So if you have an x that's in between -1 and 1, you can rewrite your function 1 over 1 minus x as this other power series. If it is not in that interval, then you can't rewrite it this way. There might be some other way of writing it, but you certainly can't rewrite it this way. Okay, so now, of course, we have these complicated things that I've just given you. But how do we come up with the power series for a function? So, for example, I just gave you this power series, but it doesn't really make sense, right? So 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus ... for absolute value of x is less than 1. Sometimes you can come up with these things algebraically. So, for example, if we wanted to check this, one way of doing this is, well, let's try checking this out. If you have, let's multiply both sides of that equality by 1 minus x. So then 1 is equal to 1 minus x times plus x times 1 minus x plus x squared times 1 minus x plus x cubed times 1 minus x, and so on. Well, you can rewrite this as 1 is equal to 1 minus x plus x minus x squared plus x squared minus x cubed plus x cubed minus x to the 4th, and so on. And so then it turns out that 1 is equal to, if we rearrange this, 1 plus minus x plus minus x squared plus x squared plus minus x cubed, and so on. And each of these goes to 0. And so therefore, this equality holds. At least, how did you get the first line? So what we're going to do is multiply by 1 minus x on both sides. So when you multiply the left by 1 minus x, you just get 1. When you multiply the right by 1 minus x, you have to multiply by each of the terms. And so this is one way of checking that, oh, well, this power series does make sense. It seems to make sense because you can multiply it and then you can transform it into something that looks like inequality, assuming, of course, that your terms out here also go to 0. So this only works when your x to the 1,000,000th term is not big. And it turns out that that's precisely when the absolute value of x is less than 1. But this is just one way of checking, and this isn't necessarily the best way of finding a power series, but it's one way of sort of intuitively understanding why these power series work. And so that's one way of doing it. Another way is you'll notice that we can substitute other things in. So let's say we have p of x is equal to 1 over 1 minus x, which is equal to 1 plus x squared plus x cubed plus x to the 4th plus dot dot dot. So then you might ask, well, what about 1 over 1 minus x cubed? Can we figure out what that is? Well, it turns out that what you can do is you can just say this is a polynomial where you've plugged in x cubed for x, and so that's equal to 1 plus x cubed plus x to the 6th plus x to the 9th plus x to the 12th, and so on. Because you're plugging in everywhere you see an x, you put in x cubed. And so that's one way of coming, if you already have a power series for a function, then that's a way of coming up with a power series for some other function. Let's try that out. So let's try adding together, oh wait, sorry, I skipped a step. So I'm basically just pointing out several ways of manipulating together functions. So we can add together power series. So for example, if you have p of x is equal to 1 plus x squared plus x cubed plus dot dot dot, and let's say this is equal to, we know this is equal to 1 over 1 minus x, then you might also ask, well, what is, let's say you have some other function, let's call it h of x is equal to 1 over 1 minus x squared. And, oh, actually, let me not do that one. Let's say this is 1 minus x cubed, which is equal to 1 plus x cubed plus x to the 6th plus x to the 9th plus dot dot dot. Well, then, what you can do is you can add these to get two things together, and so then 1 over 1 minus x plus 1 over 1 minus x cubed is going to be equal to 2 plus x squared plus 2x cubed plus x to the 4th plus x to the 5th plus 2x to the 6th plus x to the 7th plus dot dot dot. Why is the first line equal? Oh, the first line is equal here only in the interval minus 1 to 1. And you should just take that for granted for now. So I'm telling you that this is the power series for 1 minus x and 1 minus x squared. If I tell you these two power series, then you can get the power series for the sum of the two power series by just adding together by each of the terms. Okay, and sometimes you can also multiply together a power series by a polynomial, or even by another power series, but that gets pretty complicated. So let's say that I have the function, let's say g of x is equal to x over 1 minus x. Well, what is a power series for this? Well, this is equal to x times the power series for 1 over 1 minus x. So that's equal to x plus x squared plus x cubed plus x to the 4th plus dot dot dot. Oh, we haven't gotten to how we find the power series yet. So that will be in a couple steps. I'm just trying to get you guys used to manipulating power series first. So if I give you some power series, which is just some infinite sum, you can add them together, you can multiply them, and all that. And in a little bit, we'll talk about some of the different ways you can actually come up with a power series. But first, I'm going to have you all try out just manipulating these power series. So if you have one, I'm just going to tell you, let's say 1 over 1 minus x is equal to this power series. What is 1 over 1 minus 2x? Let me reset before you guys reply. Okay, so let's see. I have a couple people who are guessing A. Well, let's try plugging this in. So remember, here we are plugging everywhere you see x, you're plugging in 2x. So this is equal to 1 plus 2x plus 2x squared plus 2x cubed plus 2x to the fourth plus dot dot dot. Which is, of course, equal to 1 plus 2x plus 4x squared plus 8x cubed plus 16x to the fourth plus dot dot dot. And so let's see, people are guessing A, but you have to remember, everywhere you see an x, you plug in 2x. And so that means if you take x to the fourth power, you need to take 2x to the fourth power, which of course means that you also have a 2 to the I power. So this is equal to the sum from I equals 0 to infinity of 2x to the I power, which is equal to the sum from I equals 0 to infinity of 2 to the I x to the I, which is B over here. Okay, let's try another one. Oh, let me erase this because I wrote in the wrong place. So I'm going to give you the power series for e to the x, and we are going to derive this pretty soon. Why does it have the extra I? Oh, because this is just equal to the sum from I equal 0 to infinity of 2 to the I x to the I. When you take 2 to the 2x to some power, then you need to take 2 to that power as well as I to some power. Okay, I'm going to reset, and I have e to the x. I'm going to ask you, what is e to the x squared? So don't worry, we are going to derive this soon. We'll derive soon. So in order to find e to the x squared, everywhere you see x, you need to plug in x squared. And so this is going to be equal to 1 plus x squared plus x to the fourth over 2 factorial plus x to the 6 over 3 factorial plus dot dot dot. So what is this equal to? Okay, yeah. So once you've done this, once you've plugged in x squared everywhere you see an x, you do indeed get this is equal to the sum from I equals 0 to infinity of x to squared to the I, which is just x to the 2I by using the rules for taking powers, divided by I factorial. So we're able to, once we have a power series, we're able to manipulate it to get other power series. But now, as some of you had questions, how do you come up with a power series to begin with? Well, sometimes people might give it to you, but other times you might want to try to compute it yourself from a function. So now I'm going to give you some intuition for a Taylor series by using this example of a I'm going to give you a word problem, and I'm going to try to explain the intuition for Taylor series using this. So, if a space shuttle is moving at 10 meters per second away from Earth, how far away is it from Earth after 1 minute? Okay, yeah, so this isn't too hard, right? 10 meters per second for 60 seconds, that's going to be 600 meters. But now the question is, we had an implicit assumption there, right? Which is that it was moving at 10 meters per second, and it stayed moving at 10 meters per second. So what happens if the speed isn't constant? Let me reset before you reply. So if the space shuttle isn't moving at a constant speed, maybe it's accelerating, but yeah, it could be accelerating. So, or maybe it's decelerating. Maybe it's moving at 10 meters per second, but then the engines break, and then it starts falling back down to Earth. Exactly. So it's none of the above because we don't have enough information. So in order to predict where the space shuttle was going to be, you needed to know its speed at all times, not just at the very first time. So if the speed isn't constant, then you're a bit out of luck. Okay, so let's give you guys a little bit more information. If the space shuttle is moving at 10 meters per second initially, and it's constantly accelerating at 1 meters per second squared, how far away is it after 1 minute? So, let's see. I am actually, this is a little bit involved, so let me actually work through this with y'all. So what do we know? We know that it has constant acceleration. So we know that it has constant acceleration, which means that x double dot is equal to 1. Because the second derivative of the position is, the first derivative is the velocity, and the second derivative is the acceleration. And what else do we know? We know x dot of 0 is equal to 10. So its initial speed, its initial velocity is 10, but we don't know what its overall velocity might be. And we know its initial position is equal to 0. So how do we use all these pieces? Well, if you take the integral of this thing, integral dt, then what that gives you is that x dot of t is equal to t plus some constant. And we know x dot of 0 is equal to 10, which implies that c is equal to 10, and so x dot of t is equal to t plus 10. So now we know the speed at all times. Well, once you know the speed at all times, then what you can do is you can take another integral. So integral dt, and what you get is x of 10 is equal to 1/2 t squared plus 10t plus some other constant. Well, we know that 0 is equal to x of 0, which is equal to c2. And so this implies that x of t, the position as a function of time, is equal to 1/2 t squared plus 10t. And if you plug in x of 60, that's going to be equal to 1800 plus 600, which is equal to 2400 meters. And so because we have acceleration, you do have, why does c2 equal to 0? Oh, because you plugged in, if you plug in 0 for t, plug in 0, well then you're just left with c2 is equal to x of 0. And so and x of 0 is equal to 0, so c2 is equal to 0. So as an initial value problem, basically. Okay, yeah, so like, oh, sorry, I didn't reset the chat, but yeah, it looks like everyone's answering D. Yep, so it's 2400 meters. Well, let's reset the chat now. And what happens if the acceleration isn't constant? Then what do we do? Exactly. So we again don't have enough information. So we again don't have enough information to figure out if the acceleration is not constant. But sometimes what you can do, sort of the intuition behind this, is that if I just give you the velocity and tell you it's constant, what I'm basically saying is that the acceleration is 0. If the speed isn't constant, then in order to then you need to know what the acceleration is. If the acceleration isn't constant, well, then maybe what we can do is we can take another derivative. So the acceleration is the second derivative. Maybe you want to know how the acceleration is changing, which would be the third derivative. So if the intuition behind Taylor series is if you know the derivatives of all derivatives of a polynomial at a point, for example, at x is equal to 0, then we can reconstruct the entire polynomial. So let's give an example. Let's say p of x is equal to, I'm going to rewrite this in a funny way, 4 plus 3x plus 2x squared plus x cubed. So then p prime of x is going to be equal to 3 plus 4x plus 3x squared. P double prime of x is equal to 4 plus 6x. P triple prime, the third derivative, is going to be equal to 6. The fourth derivative is going to be equal to 0. And all the nth derivatives after the fourth derivative is equal to 0 for n greater than or equal to 4. Okay, and it turns out that even if we only know all these derivatives at a single point, so let's say that we know that P of 0 is equal to 4, P prime of 0 is equal to 3, P double prime of 0 is equal to 4, P triple prime of 0 is equal to 6, and then P to the fourth derivative of 0 is equal to 0, all the way to the nth derivative. Okay, so let's just say that we know all the derivatives at a single point, at the origin, since that's easier to work with. Well, the first thing you'll notice is that if all these derivatives are equal to 0, then the order of the polynomial, so the highest degree, is 3. Because if it had higher order, then it would have a higher non-zero derivative there. And so then what we can do is we can say, well, that means P of x is equal to some constant. It's an order 3 polynomial. And then we can just solve. So then P prime of x is going to be equal to a1 plus 2a2x plus 3a3x squared. P double prime of x is equal to 2a2 plus 6a3x. P triple prime of x is going to be equal to 6a3. And all the other derivatives are equal to 0, so we don't need to worry about those. And we also know that we can combine these two things together. So if P of 0 is equal to 4 and P of x is equal to a0 plus a1x plus a2x squared plus a3x cubed, then you know that P of 0 is equal to a0, because you just plug in 0 into P of x. And you know that P prime of 0 is equal to a1, P double prime of 0 is equal to 2a2, and P triple prime of 0 is equal to 6a3. Which implies that a0 is equal to 4, a1 is equal to 3, a2 is equal to 2, and a3 is equal to 1. Okay, so what we've shown is that if we just know all the derivatives of a polynomial at a single point, you can reconstruct the entire polynomial. And this is the intuition behind Taylor and Maclaurin series. So the Maclaurin series of a function is basically taking all these derivatives of the function and you're using it to reconstruct it as if it were a polynomial. But of course, if it's not a polynomial, it might have infinite derivatives, and so this turns out to be a para series. And the Taylor series of a function, you can do this at any one of your points. So you don't have to do it at 0. You can do it at some other number. And so the Taylor series is just, you take a real number, you take all its derivatives, you take a function, you take all of its derivatives at a real number a, and you put it together into this para series. And this para series turns out to be, under certain conditions, a para series for your original function. It doesn't always work, because your original function might be sufficiently not nice that it doesn't work out well. But if your original function is sufficiently nice, then this para series will equal your original function in an interval around that function, around that point. And note that the Maclaurin series is just the Taylor series at a equals 0, and is the para series with matching derivatives at 0 with the original function. So basically what we're doing is we're creating a para series that has all the same derivatives as your function. And our hope is that often this Taylor series will match the original function when you evaluate it at a point. So a couple of slides. The Taylor series for any polynomial is just the polynomial itself. It turns out the Taylor series matches the polynomial at all its derivatives at a point. It turns out that if a polynomial matches a para series at all its derivatives, then it's just that is its Taylor series. A Taylor series may not necessarily converge at a point, even if the function is well defined. So it doesn't always work. And a function may differ from the sum of its Taylor series, even if the Taylor series is convergent. So basically, taking these para series doesn't always work. However, for many common functions, the function and the sum of the Taylor series are equal in some radius of convergence, or sometimes even everywhere. And we're going to be talking about a couple very specific cases of functions. So for many common functions, like e to the x, sine x, cosine x, their Taylor series converge everywhere and they're actually equal everywhere. So these are very nice smooth functions, and they're sufficiently nice that you can use the Taylor series as if it were the function itself. So now that we've set up these Taylor series, now we can compute these power series that we gave as examples earlier. So for example, we have f of x is equal to e to the x. Well, we said, well, this is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So how do we figure out the Taylor series for this? Or let's use the Maclaurin series at 0. So note that d dx e to the x is equal to e to the x. So the derivative of e to the x is always e to the x by definition. So we know that f of I of 0 is equal to 1. So all the different derivatives at the point 0 are equal to 1. Plus the Maclaurin series is the sum from I equals 0 to infinity of all the derivatives at 0 divided by I factorial times x to the I. But all derivatives at 0 are just equal to 1. So this is just equal to the sum from I equals 0 to infinity of x to the I over I factorial. Isn't d dx e to the x equal to e to the x times the derivative of x? Yes, it is. What's the derivative of x? The derivative of x is just equal to 1. So yes, it is times 1. But so you get d dx of e to the x is equal to e to the x. Yeah, it's 1 in this case. And so there is a times 1. But that doesn't change anything. In fact, this points out some of the other cool things you can do with these power series. So if I were to give you this power series for e to the x, it turns out that if you take the derivative of the power series, you also get the original answer back. So if you were to take d dx, so this is an aside, it's not super important, but it is something you may see in a physics class, so I'm going to go ahead and mention it. If you take d dx of this power series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, going on to infinity, this is actually equal to, well, 0, because the derivative of 1 is 0, plus 1 plus x squared divided by 2 factorial. Well, that's 2 times x over 2 factorial, which is just x over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, and so on. And so it turns out that this is indeed e to the x here, and this is also indeed e to the x here. So if you have the power series, you can actually say something about the original function that its derivative is equal to itself. Because you can apply these operations like derivatives to power series as well. Okay, let me give you an example of another very special function, cosine of x. What is the Maclaurin series for f of x is equal to cosine of x? Well, remember the Maclaurin series is the sum from I equals 0 to infinity of the ith derivative at 0 times I factorial divided by I factorial times x to the I. Well, we need to know what all derivatives are, right? So if we have f of x is equal to cosine x, f prime of x is equal to minus sine x, f double prime x is equal to minus cosine x, f triple prime of x is equal to sine x, and so on. And it turns out that this repeats. Could you explain the first part again? This part? So that's the definition of a Maclaurin series. So that is the definition that we gave on this slide here. Oh, on the last slide? Let me go through this cosine example again, and if it's still confusing, then let's go back. Since I'm going to give you, yeah, so let's finish this example, and then we'll go back to the other slide, okay? So this is the definition of a Maclaurin series. So we want to know what this is. And note that we have several different pieces. We have this piece, the top piece here, fi f to the ith derivative of 0. So what we're trying to do is we're trying to compute all derivatives of f. And so that's what we did down here. So we computed all derivatives of f of x. And now we want to evaluate it at the point 0. So f of 0 is equal to 1, f prime of 0 is equal to 0, f double prime of 0 is equal to minus 1, f triple prime of 0 is equal to 0, and then it turns out if you keep on going, f to the fourth derivative of 0 is going to be 1 again, and then 0, and then minus 1, and so on. Because this repeats. So now we know all derivatives of cosine of x at the point 0, at the point x is equal to 0. So we can write this all out. So now we can write out this entire series. Well, this is going to be, well, the first term when I is equal to 0, that's going to be 1. Because x to the 0 is equal to 1. The first derivative, so f of 0 is also 1, and 0 factorial is equal to 1. Plus 0 divided by 1 factorial times x, plus minus 1 divided by 2 factorial times x squared, plus 0 divided by 3 factorial times x cubed, plus 1 divided by 4 factorial times x to the 4, oh, sorry, go back. The fourth factorial times x to the fourth, and so on. Okay, all we're doing is we're plugging in these values for the derivatives into this infinite sum. Okay, so because this infinite sum, another way of writing this is this infinite sum is equal to f of 0 divided by 0 factorial times, which is just f of 0. So this is just equal to f of 0 plus f prime of 0 divided by 1 factorial x plus f double prime of 0 divided by 2 factorial x squared plus f triple prime of 0 divided by 3 factorial x cubed, and so on. Okay, so that's all we're doing here is we're substituting these values in to figure out what this Maclaurin series is. And if we simplify this a little bit, this ends up giving you 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6. Oh, I keep on switching slides, which is a little bit vexing. Plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial plus x to the 8th over 8 factorial, so on. Isn't it going to go on forever? Yes, it is. That's the whole point of these power series. They go on forever. Sometimes you'll see this written out in a slightly different way. Because it does go on forever, you can write this as another infinite sum, I equals 0 to infinity minus 1 to the I times x to the 2i over 2i factorial. And yes, so this is an infinite sum, and that was the whole point, right? Because cosine has an infinite number of derivatives that are non-zero, this will go on forever and it won't ever be a polynomial. This is what we were saying earlier on about how cosine and sine aren't polynomials, even though they are nice, smooth functions. And going back here, that's what we were doing here. Because what we did here is we did the same thing with the Maclaurin series. So this was equal to f of 0 plus f prime of 0 divided by 1 factorial x plus f double prime of 0 divided by 2 factorial x squared plus f triple prime of 0 divided by 3 factorial x cubed, and so on forever. But we know what all these derivatives are. They're just all equal to 1, and so you're just left with this thing. So that's how we got the Maclaurin series for e to the x. Okay, let's have you all try it out, and I seem to be running over on time for this part of class. That's alright, we're getting close to the end of class anyway. So I'm going to ask you, what is the Maclaurin series for f of x is equal to sine of x? And let me reset my chat quickly. And so again, let me give you the setup again, and so hopefully you guys can work it through. So the setup is the Maclaurin series is equal to I from 0 to infinity of f the ith derivative of at 0, I factorial x to the I, which is equal to f of 0 plus f prime of 0 plus f double prime x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed, and so on. So if the derivatives are the same, then the Maclaurin series can be solved. It's not infinite, but if the derivatives are all different, then it just goes on forever. Well, I mean, the Maclaurin series always goes on forever, but just sometimes the derivatives repeat, or they are all equal to 0, and so it's easy to write down. Okay, so let's see what we have. We have a lot of people guessing B and D, it looks like. So, well, let's figure out what this is. We have f of x is equal to sine x. So then f prime of x is equal to cosine x. F double prime of x is equal to minus sine x. F triple prime of x is going to be equal to minus cosine x. And f to the fourth derivative of x is back to sine x, and so on. And so that repeats. And so then we have f of 0 is equal to 0. F prime of 0 is equal to 1. F double prime of 0 is equal to 0. F triple prime of 0 is equal to minus 1, and so on. So we plug that in. That's equal to 0 plus 1 times x plus 0 minus x cubed over 3 factorial, and so on. And it keeps on going. And so it turns out that's going to be plus 0 plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. And so the answer here is indeed D, which it looks like a reasonable number of people managed to get at the end of the day. Okay, and let's finish off this half of class with the payoff for all this, which is I gave you this magic equation last week. Euler's equation, e to the ix is equal to cosine x plus I sine x. Why is this true? Now, there are a couple different ways of trying to figure out why this is true, but the one way that we now have access to is we can use power series to prove this. So notably, we have e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. I'm messing this up, sorry. Let me rewrite this. Plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial, and so on unto infinity. So now, what is e to the ix? E to the ix, well, we just have to plug in ix everywhere we see an x. So you get 1 plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the 4th over 4 factorial, and so on. And so this turns out to be 1 plus ix plus, well, what's I squared x squared? I squared is equal to minus 1, and so this is just going to be minus 1 over, minus 1 over 2 factorial x squared. Oh, I keep on clicking randomly, and it's really vexing. So plus minus I times x cubed over 3 factorial plus x to the 4th over 4 factorial, because I to the 4th power is just equal to 1, and so on, okay? So what we've done is we just plugged in ix everywhere we see x, and now we've multiplied it out because we know that I squared is equal to minus 1. You can rewrite this by collecting all the terms without an I and all the terms with an I. So when you write this out, you end up getting 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on, plus I times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on, which is precisely equal to cosine of x plus I sine of x. So these are some of the magical things you can do with power series. So we gave you this really crazy equation, the Euler's equation, and it turns out that if you just use Taylor series and Maclaurin series, you add them all together, and that proves that e to the ix is cosine x plus I sine x. And I think that's where I'll end for the first half of class. Let's take a... we are running low on time, aren't we? Let's go ahead and take a 7-minute break and be back at 1:35. And then the second part of class is a lot shorter, and so then we'll finish up there. So I'm going to stop the recording here.